Hello friends, we were discussing about series resonance of a bandpass filter, and this is the circuit whatever we have discussed in our previous video. Now in this video I am going to show you two very important things related to this circuit. Okay, let's check. Number one is I have shown you the graph for the impedance of this circuit for different values of omega, and the graph is this one. As the resistance, inductance and capacitance are in series in that circuit, so the expression of equivalent impedance Z equal to R plus j omega L minus j by omega C, or plus 1 by j omega C, you all know. By replacing 1 by j by minus j, we get this expression, that is Z equal to R plus j omega L minus j by omega C, and we got this curve. Okay, this is a non-symmetric parabola. I explained in my previous video. This is the graph of the impedance Z for different values of omega. Okay, this thing you all know how the graph came, why it is non-symmetric from my previous video. Now one very important question here comes, that why I have plotted the Z mean as R. Okay, see here this portion. See, the minimum value of the Z for any value of omega is R. Okay, so why this is happening, I will show you. See, that is the question, why Z minimum equal to the series resistance. Okay, see, this is the circuit where R, j omega L and 1 by j omega C were connected with V input of j omega. This is the same circuit in frequency domain. Now see what is happening. We got Z equal to R plus j omega L plus 1 by j omega C. By replacing 1 by j by minus j, we get this expression, Z equal to R plus j into omega L minus 1 by omega C. Now by taking magnitude, mod of Z equal to root over of R square plus omega L minus omega 1 by omega C square. Okay, now see what is happening, why this, if you take this expression, that is mod of Z equal to root over of R square plus omega L minus 1 by omega C square, see at the resonant frequency what happens, omega naught L equal to 1 by omega naught C, and these terms becomes 0. Okay, because omega naught L cancels 1 by omega naught C at resonant frequency omega naught. Okay, so we will get at resonant frequency mod of Z equal to R. Now why it is written as mod of Z minimum? Okay, it is clear from your basic concept in mathematics. Here mod Z equal to root over of a square plus b square. So b square term, suppose you consider this term as b square. Okay, so b square, this term obviously greater than equal to 0, because we all know that any square value is always greater than equal to 0, and this is a square. Okay, so now is mod of Z equal to root over of a square plus b square, as b is greater than equal to 0. Suppose a is not variable. Okay, a is constant, so basically the expression is root over of a square plus b square. Clear? Now see, b is variable and b square is greater than equal to 0. So what will be the minimum value when b square equal to 0? That means mod of Z equal to root over of a square is the minimum value, and that is equal to a. Okay, here a is equal to nothing but R. Okay, so that the Z minimum is R, because this whole term can be minimized to 0, not less than that, so that at the resonant condition when these whole terms become 0, Z of minimum we get as R. Okay, I hope by the just simple concept in mathematics you can clearly interpret why this resistance, the impedance is minimum at resistance R. Okay, and one more question may appear in your mind, that is this one. This circuit we call as resonant circuit whenever omega naught L equal to 1 by omega naught C, that is the impedance offered by this the inductance and the impedance offered by the capacitance become same, then we say that this is called resonant frequency omega naught. So what is the significance of the word resonance? I will explain. This also I have not mentioned in my previous video. So what is the meaning of electrical resonance. Okay, in electronics, what is the meaning of the word resonance? Okay, in your class 11 in chemistry course, you have studied the resonance of benzene. Okay, in chemistry you have studied the canonical forms. Here this bond goes here, this bond comes here, and this bond comes here. We get, so then we get this configuration. So basically, as the bonds are rotating, so that we get this canonical form. That is here we represent this, the inside bond by circle. So this is the resonance or canonical form of benzene. But is the same resonance is indicated by resonance in electronics? No. In electronics, resonance is something different. See, in electronics, the resonance is, what is the resonance? AC circuit made up of resistor, inductors and capacitors are said to be in resonant circuit when the current drawn from the supply is in phase with the impressed sinusoidal voltage. Okay, that what it means. See, from the circuit you will get idea. When the current which is flowing through this circuit is in phase with the input voltage, then we say that the circuit is in resonance. When it is possible, when the circuit is purely resistive, that is when Z equal to R, because in case of resistance only, the current flowing through the resistance is in phase with the input voltage. In inductance and in capacitance, there is 90-degree lead or lag, so that current and voltage are not in phase in case of inductor and capacitor, but in case of resistor, the current is in phase with voltage. This thing you know from your physics course. So basically, whenever this circuit will be purely resistive, then in that case we say that the circuit is in electrical resonance. And when a circuit is acting, when this series RLC circuit acts like a purely resistive circuit, when it is in resonance, that means when omega naught equal to 1 by root over LC, then the circuit is purely resistive. So that we say that the circuit is in resonance. Okay, here the resonance does not mean that the chemical bonding, like that is different in chemistry. Here in electronics this is different. And one more thing. So basically, just now I told at resonant frequency Z equal to R, that is purely resistive. And one more thing, just as you know that in resonance the natural frequency matches with the external frequency. That is, if you interpret in such a way, so basically resonance is some situation when some exceptional things happens. You all know. So like when you are walking through a bridge, suppose a group of army is walking on a bridge. Okay, when they parade simultaneously in a same periodic manner. So when if some case arises when the periodic movement of the soldiers, the frequency matches with the natural frequency of the bridge, then the bridge starts oscillating in a very high manner. Okay, so as the bridge start oscillating, then it will create some problem in that configuration. So the civil engineers make the bridge in that manner. Okay, that is different. So basically what I mean to say that resonance is a situation when you can expect some exceptional changes in behavior of circuit performance. Like in real time, when some singer sings, you may have seen this thing in TV shows, that one singer is singing and at very high frequency of his voice, one glass which is kept near him or her breaks. Okay, so what happens, that the two frequency matches, the voice frequency of the singer and the natural frequency of the glass matches, so that it breaks. So at resonance, every time some exceptional change is there. Okay, in real time, so obviously some exceptional change must be there in circuit application of resonance also. Then that name, the resonance name, will be signified. So what happens, what is the exceptional change? This thing you know, that this is the blue color curve is the impedance graph for different values of omega, and at omega naught the Z is minimum. So I have shown this, and it is equal to the R. And see the current, as the current is inversely proportional to Z, so that what is the current graph? Current graph is just inverse. That means at the resonant frequency the current is maximum. Okay, This is the exceptional thing. At resonance, the current of this RLC circuit becomes extremely high, so that it is called resonance. This is the exceptional factor in resonance. Okay, so I hope I have made a clear idea how the resonance name came in the picture of the series RLC circuit when omega not equal to 1 by root over LC. So what happens when omega not equal to 1 by root over LC? In that case, the Z equal to R, so that the impedance offered by inductor and capacitor cancels each other, and the current is in phase with voltage. This is the in terms of the this is what I can say in terms of the what we know for resonance, like in terms of the definition. Okay, but in actually, if you want to think in some real time manner, so the exceptional change is basically the current becomes very high at this resonant frequency. Okay, so I hope it is clear to you what is resonance, what is meant by resonance, why the impedance is minimum and that is equal to the resistance. Okay, why not other values? I hope I have made this clear idea. Thank you for watching. If you have any doubt, you can ask in comment section. Thank you.